Okay. Uh, Hi everyone. I just hope I'm audible. So yeah, welcome to the week 11 live session on the course Semiconductor Devices and Circuits, NPTEL NOC24 EE-143, that is taught by course instructor Professor Sanjeev Sambandhan from IIC Bangalore, and I'm the TA for this session. My name is Yavar. I'm a PhD student at IIT Kanpur. So the schedule for my sessions, as usual, has been and will be, unless informed. Otherwise, it will be every Sunday, 5 p.m. to 7 p.m. Okay, and these are my details that you can use to reach out to me. Okay, so there were a couple of email queries. Uh, I'm planning to address them after week 12, right? We'll have an extra session after week 12. So I'm planning to address them in that session, okay? Because I need some content to cover in that extra session. So I'm planning to keep those queries as a content in addition to my already planned content for that extra session. Okay, I hope that would, I mean, do it. So yeah, then we have, as usual, the guidelines. In case you have any query, you can either use the chat window or you can just raise your hand, okay, directly, and I'll uh, unmute that person. So, however, when you don't intend to speak, please make sure that your microphones are muted. Okay, please ensure that. And I would appreciate your cooperation to make this an interactive session, although I need some students for that. Let's hope some students would join as the session progresses. So yeah, please keep pen and paper handy along with a scientific calculator, right? Because uh, in the numericals and problems, that calculator would come in handy, right? And pen and paper as well. So yeah, and then once this session finishes, then the session recording link and the lecture notes will be shared by the NPTEL course team. Okay. So yeah, the prerequisites include the last week's lectures, which covered the following topics: the MOSFET as a switch, the amplifiers using the MOSFET, circuits, the frequency response, and the noise. Okay. I'm assuming that you all have already attempted the assignment 11, okay, before tuning into this session. Or I mean, even watching this session in the recorded form. Please make sure you already attempt this assignment 11 before. So, brief recap. Mm, I mean, we have topics like MOSFET as a switch, amplifiers using the MOSFET, circuits, frequency response, noise. Uh, since we don't have many students in the meeting, so I'm assuming uh, there are no doubts regarding these topics. So what we'll do is we'll start the problems directly. Will that be fine? There is one student in the meeting though. Uh, Prasad Rao, I guess, right? So yeah. So Prasad Rao, could you just type in the chat if that would be okay, since you are the only one in the meeting? Can we start the problems directly then, if there are no doubts? Also, please confirm if I'm audible. Nobody confirmed it yet. Okay, sir. Okay, audible. So yeah, I guess then we are fine and good to go. So with that, I'll be starting the first problem. Sorry. So you need to calculate the approximate magnitude of the small signal voltage gain. Okay. Assumption is that you need to ignore the body effect and the channel length modulation. Okay. So it's given that GM is 2 millisiemens and RD is 15 kilo ohms. right? And this is the circuit for consideration, and just compute what is the magnitude of the small signal voltage gain. Uh, I'm hoping many of you would have recognized that this is actually a common source amplifier with source degeneration, right? So how does the gain get affected? How does the gain I mean, how is the gain affected in common source amplifier with source degeneration configuration? Anyone? I mean, I should not address as anyone. There's only one student in the meeting. Prasad Rao, any idea? How is the gain affected? Sorry. See, what I'm trying to say is that uh, the impedance that you would see is, yeah, how does that affect? Impedance seen is your 1 over GM, right? So my way to make its equivalent would be, we'll have this VDD, right? And you'll have this RD. This is your V in, right? This is your V out. And this is your 1 over GM, right? Impedance. And what else? Yeah, that's it. Sorry. So if there is a current, say suppose ID that's flowing, so what happens is our degeneration resistor, right? This degeneration resistor, it is in series with the source terminal, right? So as your V in increases, uh, so does this ID, right? And when ID increases, the voltage drop across this degeneration resistance increases, right? And what does that result in? So what happens is you're part of change in V in, right? Your delta V in, right? I mean, a part of it starts appearing across this degeneration resistance as well, right? Uh, Rather than this gate source overdrive, right? So it makes the variation in the ID smoother, right? So ID would have, I mean, smoother variations in nutshell. So in other words, your gain would be a weaker function of GM, right? Why? Because your part of change in V is now appearing across this degeneration resistance, right? So we would expect gain to be now a weaker function of GM. Let's see that now mathematically. So yeah, now what is gain? Wait, let me take this to the right extreme. I can do one thing. I'll take this here. Let's start the calculations from here. So your gain is GM RD whole divided by your 1 plus GM RS, right? Then Now, I mean, by RS, I mean this regeneration resistance, right? That is 1 over GM, right? So I can write GM RD whole divided by 1 plus GM times here 1 over GM, right? And that would be GM RD whole divided by 2, right? So as we expected, the gain has now become a slightly weaker function of GM than in absence of this degeneration resistance, right? So now let's plug in the numbers. What is GM? GM is your 2 millisiemens and Siemens, and this RD is 15 kilo ohms, right? Sorry. So this would be equal to, what is RD? RD is 15K whole divided by 2. So which is equal to, just a second. Okay. I got the answers in the chat, 15, which is the correct answer. Thanks for answering. This would be 15, right? So our gain is 15. So that is what we were asked to compute. I mean, ignore this. I mean, this is the correct answer. Okay. Now, is this fine? Is there any doubt in this question? I have two students, so if none of them have any doubt, I'll proceed. Okay, fine. I'll be proceeding. So the second question is following. You will consider this MOSFET topology that is given below. You'll assume that this MOSFET is in saturation, okay? And the current source is ideal. It's given that GM is equal to this, and your output impedance is 12K ohm, RS is 0.8 kilo ohm. And you need to find what is the magnitude of the small signal voltage gain. This is pretty straightforward. So I'll expect you to answer this one. I'll wait for 3 to 4 minutes. Okay. I'll wait for you two guys to answer this. And if not, then I'll show it myself. Okay. Your time starts now. 3 to 4 minutes. Break. Okay, I guess that was sufficient break. So one answer in the chat from Prasad Rao, and he says that this gain would be, I mean, the magnitude would be 12, which is in fact the correct answer. Uh, that's good. You were able to solve it yourself, but I guess I'll still show it for the sake of others because you only have two students and one of them has answered, and most of the students watch it in the recorded form anyways. So I'll proceed to solve this one. So uh, I mean, your current source is ideal, right? Your current source is ideal, and to measure this small signal impedance, you need to consider the small signal equivalent circuit, right? With input set to zero. I mean the following. Sorry. V out. Sorry, wait. Yeah, sorry for the interruption. So yeah, I mean let this be n0 and am I audible? I'm audible, right? Okay, fine. So yeah, then this is your node A, right? And yeah, what is the output impedance? That is your R0, right? Yes, I should write that as well. That output impedance is R0, and your gain would be what? Your gain would be, I mean, the magnitude of that would be GM times R0, right? And your GM times R0 would be equal to uh, I mean R0, right? R0, and that is equal to what is GM? Your GM is equal to 1 milli, and your R0 output impedance is 12K, right? And that is equal to 12. So, I mean, I was interested in magnitude, right? So that's why this would be 12. So the correct answer is this one. Yeah. If is this clear, right? I mean, one of you were able to reach to this answer yourself. So I guess this was straightforward. Why did we ground the gate? We grounded the gate because we were interested in a small signal equivalent circuit with input set to zero, right? Because we had to measure the small signal impedance, right? That's the way we measure it. This is small signal impedance, right? That is the reason we set input to zero in the gate. Is that clear? So V in is not small signal input. Small signal input. Now, I mean, this is the way we compute the small signal impedance, right? When we are to compute the small signal impedance, we set the input to zero, right? That's the way it usually is, right? Now we can check it later if you still have any doubt. Thought this is clear. Okay. So we'll move on to the third one. So the third one is following. In single stage common source amplifier, the transistor is biased in such, I mean, it's biased such that this transconductance parameter is 5 milli. The load connected to the amplifier is 1 kilo ohm. The output impedance looking into the drain of the transistor is 50 by 51 kilo ohm, right? What is the small signal gain of the common source amplifier? So I'll just, I mean, draw this topology and then you'll try to compute it. So this would be VDD and I'm having this load of 1 kilo ohm, right? So that would appear here, your 1 kilo ohm load. And then right. And your impedance seen that is given to be 50 over 51 kilo ohm, right? And this is the net output impedance. Okay. Okay. Now, how will you compute the small signal gain? Minus GM times R naught, right? And minus GM times your R naught would be, this is the net, right? This is your net output impedance. So your gain, I mean magnitude of that would be GM times R naught, right? And that is equal to what is GM? 5 milli. What is R naught? 50 by 51 kilo, isn't it? So that is gain. So your gain would be equal to 4.902. Yeah, 4.9. So that finishes up this question number 3. Then what about this question? This is an easy one. So, and this has been taught in the lectures as well, right? How to compute the, I mean, gain of amplifiers connected in cascade, product of the gains. Yeah, right. Okay, let me just conclude this question as well. So, when two amplifiers, say of gain, your A1 and A2, when they are connected in cascade, right? The overall gain is your A1 times A2, right? And yeah, 24.029 is the correct answer. Glad that you computed that. So let me finish this. So in this case, in this case, our overall gain, if am I audible? Wait, yes. Uh, I mean, is my, has my voice been affected? Actually, uh, my buds got disconnected. So should I continue or should uh, it's clear. Fine, then I guess I don't need to. Fine, I'll continue then. So overall gain. Okay, thank you. So overall gain is your 4.902 times 4.902, and that is equal to 24.029. Right. So this was an easy one. Let's move on to the, okay, this I'll keep as an homework for you. So this question is homework. Okay. Take this as a homework from this live session. We can discuss this one in the next one, probably. Okay, would you want to try this one right now? Or should I move to the sixth one? Okay, please try. So, but I'll only discuss it in the next session. Reason being, I want all of you to try it first because we only have 2 students, right? And many of the students watch it afterwards in the recorded form. So you guys can attempt it and
I won't, I won't ask you about the approach, but you can share the answer, the final answer, if you are able to solve it. Do it. I'll resume at 5:40. Okay. Uh, you guys have 6 minutes. Please try this out.
All right. I guess that was sufficient time uh, for you guys to attempt it in this live session. We'll be now, I mean, moving ahead to other problems, right? Uh, let's have a discussion on this one uh, in the next session, probably, or some other time, or our mail. So, uh, yeah, then we have the question, sixth question, right? You need to consider the circuit shown below that has following specifications. Your RD, right? Sorry, your RD is 6 kilo ohms, right? Your Kn is 0.1 milliampere per volt square. Your Vt is zero point 0.8 volts for both the MOSFETs, right? For both the MOSFETs, you'll use Vt as zero point 0.8 and Kn as zero point 0.1 milliampere. And then, I mean, zero point 0.1 milliampere per volt square. And you'll be ignoring the channel length modulation, right? And if your V1 is 5 volts and your V2, where is V2? This is 0 volts. The value of the current through this resistor RD, what is this current, right? This is what you need to compute. So how should we proceed on this one? Should I first wait for you guys to attempt this and then uh, I should show it myself, or should I just go ahead and start solving it? Any suggestions from you two guys? Would you be interested in attempting this yourself first? Okay, I should go ahead. What about you, Prasadra? Should I go ahead and solve it? Go ahead. Okay, fine. Then I'll be going ahead and solving it. So see, your V2 is 0 volts, right? Your V2 is 0 volts. So what about your then this uh just a second. If your V2 is 0 volts, then I mean this M2 would be off, right? Won't that be the case? I mean, can I conclude that VGS is 0? So I'll say that uh, my M2 is off. Reason being, my VGS for this M2 would be 0. So once that is done, so see, MOSFET would be operating in linear region, right? And see, wait, I'll first draw the simplified one. So see, I'll be left with this one. I'll have this VDD that is 5 volt, and then I'll have my RD, sorry, that is 15 kilo ohm, right? And then I'll be only left with this one, isn't it? Because this is anyway off. So your M2 is off. So only I'll be only drawing this M1. This is your V1 and this is your M1. This is your PO and yeah, and this is 5 volt. That's pretty much it, right? So see, now your MOSFET, it's operating in linear region, right? And you can validate this by checking the current that is flowing uh, for saturation, and then checking the value of VO, and the condition that VO is greater than I mean V1 minus VTH, right? Because that would be your VGS minus VTH in this case. And uh, so your I would be following. Your I would be your gain, your VGS minus VTH times VDS minus VDS square for 2, right? And uh, what about this? Your VDS? Your VDS is simply 5 minus your I times RD. And you can plug the value of RD as 15 kilo ohm. That is 15. So the point that I'm trying to make is, if you'll solve it for I, right? Uh, Firstly, can you solve it for I? You can, right? Why? Because you have got two equations with two unknowns, right? So, I mean, is this clear? Let me see the chat. Okay. Right. I mean, I'll only have two unknowns, right? The I, this I, right? Now my IR would be the ID1, right? This is one unknown. And what is the other unknown? I mean, these are my two equations, right? This and this. What are the two unknowns? VDS, right? This is the other unknown. Rest of the quantities I know, right? So I can solve it, right? Because I have got two equations with two unknowns. You can solve this system of equations. So on solving, I'll leave this as an exercise for you. Yeah, VDS and I. So on solving, uh, you'll obtain I as 0.314 milliamp. Yeah. Please verify this, okay? That you indeed get this I as this. So, and that was the only thing that uh, you were supposed to compute, right? Your I, this I is this IR, which was flowing through this RD. I mean, how did we conclude that the device is in saturation? Okay, for that, uh, okay. So if the device is in saturation, firstly, I assumed that the device is in saturation, right? If I assume that the device is in saturation, I can use this equation, right? Can I use this if I assume the device is in saturation? No, wait. I mean, this is the linear one, right? This is not the saturation. I assumed that you confused me. I assumed this device is in linear region, right? This is operating in linear region. So correspondingly, I used the equation that is valid in the linear region, correct? Fine. So then correspondingly, I'll get the value of VDS, right? Which is nothing but my VO, right? Because VDS is VO minus this. Then I'll see VO and compare that with your this, what should I say? Your V1 minus VTH. Why? Because V1 would be the VGS in this case. If this satisfies the condition of, I mean, linear region, then I'm right. If not, I'll use the saturation equation. Is this clear now? I'm also, in other words, I'm leaving this as an exercise for you, right? Go ahead and verify if I can indeed use this linear equation or not. Okay, turns out you can, but still, uh, I mean, to quench your curiosity, you can uh, do this exercise, and you should do this exercise. I mean, if I were to evaluate this question, there should be, I mean, an explanation of why indeed this assumption of taking this MOSFET operating in linear region is valid. For that, you need to show the relative values of your V0 and your VGS minus VTH. Your VGS minus VTH in this case is V1 minus VTH, right? Because VGS is V1. So yeah, I'm pretty confident you can do that. So see, on solving, you'll get the value of both VDS and I. I is this one. And say suppose you were asked in the question that compute the value of VDS. I mean, that could be one more, and you can just plug I here and get the value of VDS, right? That is something trivial, but okay. So is this sixth question clear? I hope it was clear and why we assumed it to be operating in linear region. Shall we move on to the next question then? Okay, fine. Got the green signal. So the next question is following the small signal resistance, that is your dVB by dID in kilo ohm, offered by your N-channel MOSFET M shown in the figure below at a bias point of VB equal to 2 volts is uh, is this one, right? And okay, the device data. Okay, we need to compute the small signal resistance, right? dVB by dID for this N-channel MOSFET, right? It has, I mean, this is set to 2 volts, right? I mean, this is the bias point at which we need to compute the small signal resistance. And your transconductance parameter Kn is 20 microamps per volt square. Your threshold voltage is, I mean, VTN is 1 volts. And you can ignore the body effect and the channel modulation effects. This is also a simple question. And can you just try this quickly? I mean, the previous question needed some thinking. That's why I went ahead and showed it directly. But can you give it a try? Device is in saturation. Okay. And why is that the case? Why is that the case? Sorry. VG is equal to VD. Yeah. So how will you then compute the small signal resistance in this case? It would be your small signal resistance is what? That is your 1 over GM, right? So in other words, you need to compute GM. And once you'll take the reciprocal of that GM, that would give you the small signal resistance, right? Is this clear? Okay. So since, I mean, the broad approach idea is clear, I'll go ahead and show you the values so that we all are on the same page. So see your Kn, that is equal to 20 microamps per volt square. Your VTHN is 1 volts. And what else? And by definition, I mean, in this case, the small signal resistance, that is equal to 1 over GM, right? And we already discussed the operating regime of this device. and concluded that this would be in saturation. So this would be mu n Cox W by L, your VGS minus VTHN, right? And what is VGS in this case? That is VB, right? Minus VTN, right? So this is nothing but 1 over mu n Cox. What is mu n Cox? Mu n Cox W by L, this particular quantity, that is equal to 20 microamps. I mean 20 micro amps per volt square. And then VB minus VTN, that is equal to 2 minus 1, isn't it? So that is equal to, that would be 50 kilo ohm, right? So the answer is 50, right? Why? Because we were supposed to compute the small signal resistance in kilo ohms. So is this clear? What if we take into consideration body effect also? What change would it make in solving the problem? I'll leave that as an exercise. Okay. Try this out. That is something that you can explore. I mean, do this as an exercise and then we can have a discussion. Okay. I mean, consider in another, I would say, variant of this question, consider the body effect. I mean, you can assume the values, you can assume some practical values and go ahead and compute the answer and then compare the relative answers. Also do it for the channel length modulation as well. Okay, do it for both and then we can have a discussion. Fine. Okay. With that, we can move to the last problem for this session. So consider the following circuit shown. Your W by L of your M1 is 40 over 2. The W by L of M2 is 8 over 2. If you ignore the, how can you find out the small signal voltage gain? Okay, so see, what I can say is ID would be same for both the devices, right? For M2 as well as M1, I'll have same current flowing, right? There would be common ID for both. And I know that your gain, that would be GM1 times GM2. Sorry, I mean your 1 over GM2, right? So yeah, it would be 1 over GM2. And then uh, I can write following, right? I can write this is square root of 2 mu n Cox W by L1 ID whole divided by square root of 2 mu n Cox W by L2. ID is same. I'm also assuming this mu n Cox for both these devices is also same. So I'll be left with the ratio of the squares of their W by L ratios, right? In other words, this is what I mean. Gain is equal to square root of W by L on square root of W by L, right? And this would be equal to here 40 over 2 is square root of 20, 20 over 4, which is square root of 5, and that is equal to what is square root of 5? 2.236, isn't it? Done? So yeah, with that, I mean, this was the last problem for this session. Do try this out, okay? Did you guys try out this problem 5? You did not report answers. Was anyone able to solve it? Don't discuss the approach, but just tell me the answer. If at all you were able to find one. Okay. No, sir. Okay. Fine. I mean, have to try again. Fine, it's fine. Just try it out. I mean, you'll anyway get the slides as well. Try it out. And after all of you try this out, we can probably discuss this one, right? Yeah, that's it. That's all I have for this session. And again, just like I mentioned at the beginning of this session, some students had queries over email. So what I plan to do is I plan to discuss them in uh, the session, the extra session that is planned after week 12, right? This was week 11 session. We'll have one more session, week 12 session. And after week 12 session, we'll have an extra session in which uh, it would be mixed, right? That would be sort of a summary session, right? And I plan to address those queries in that session. I hope that would, I mean, be fine with all. So yeah, thanks for tuning in. Uh, Fine. Any other details that you wish to discuss apart from queries or any feedback in general that you would wish to discuss? Please unmute and you are free to provide me feedback.
Hello, sir.
And I mean, yeah, please go ahead.
So it
Hi,
would be
Sandeep.
better if we could be provided with the lecture slides for week 10, 11, and 12.
Week 11, week 12. I mean, I do provide the lecture slides, right?
So I meant the one taken by sir. The
Okay, the
lecture
one
slides
taken
weren't
by Sir.
uploaded.
Okay. I understood. Yeah, I understood what you are trying to say. The thing is, even I don't have access to them. If I would be having access to them, I would have shared that. For that,
I have
did
raised
you
the issue
raise?
in the forum
Okay,
also,
you
but
raised it. Okay,
didn't
okay,
get any
okay.
reply.
Also, you do receive the feedback form, right? For the not for this live session. You get the feedback form for the other thing as well, right? For the
Yes, weekly.
yeah, do mention that point in that. They'll probably look the feedback form more seriously,
Okay.
in my opinion. Yeah, please mention that. You all of you can just mention this. Any other
So
feedback that you would wish to discuss on
yes,
how
sir. So
this?
once we have
Yeah.
taken this course, would you
Hmm?
recommend any publications or any journals we could refer to improve
Any
knowledge in this field?
applications? Any applications?
Publications, sir.
Publications. Oh,
Yeah.
publications. Fine. So once you go through this course, could you tell me, are you a PhD student right now?
No, I just completed my graduation.
You completed your graduation. Okay.
Yeah.
So what I would suggest you is, since this is a semiconductor device and circuits course. Are you interested in circuits or are you interested in devices? You'll probably be interested in devices. That's why you ended
Yeah,
up taking this
devices.
course, right? So, journals that you can refer to, I mean, you can do one thing. Uh, there is monthly issue of transactions on electron devices and electron device letters. Both for both the publisher is IEEE. So you can do one thing is you can see what what is the trend, what are the new papers that are getting published. I'll assume you have access. I'm assuming you have the IEEE membership because you'll be needing that to access them. Uh, and once you uh, go through the monthly issues uh, and start reading the papers that you are interested in. It's not necessary that you'll end up reading all the papers. Read the papers with titles that interest you. Okay, read only those papers. So once you do that, shortlist them and go through them in depth. And those papers will have some references, right? And then you can probably, that would be some starting ground, right? And then this chain reaction would start. And then you'll end up, reading some reference paper and all those things. I hope I made some sense.
So any recommendations about any specific author?
Author?
Yeah.
Okay.
Would you recommend any
Author.
specific author that we must regularly follow?
Are you interested in device applications or, by the way, by any means, are you interested in device modeling? No, probably not.
So actually, I did not understand the meaning of that.
Yeah, I understood. I understood. See, the thing is, your research area should first be finalized before, following a particular author. I mean, I can tell you many authors that you can follow, but the thing is, those would be the ones that I follow because my field is a particular research area. Are you getting the point? Once your
Okay.
research area is finalized, then you can follow the pioneers of that particular research area. So before following any particular author, it's important that you finalize the research area. Although, I'm assuming you are interested in semiconductor devices, right? But still, the semiconductor devices is also a very vast area. You need to still channelize that particular domain.
Okay. So
Fine.
apart from modeling, what else do we have?
Apart from modeling, there is this device characterization, there is fabrication that you can get into, and uh, photonics is also there. Uh, there are many domains, and there are some domains that are particularly oriented towards applications, right? For example, photonics is there. What else? Uh,
Solar cells, photovoltaic cells.
Sorry? Yeah. Those as well. I mean, there are many things. All those come under the bracket of this semiconductor devices because at the end of the day, those are semiconductor devices, right? And also this your GaN HEMTs, right? Your 3, 5 uh, based HEMTs. So that is also one area that one can look into because I mean, or something like, for example, the devices that are particularly used for cryogenic applications. That is also one domain that you can look into. So yeah, a survey is important, and for that, feel free to mail me regarding that. I mean, if you have some shortlisted areas that you are, trying, that you are deciding upon, I can give you a gist of that. Because this area would involve this work, and area two would involve this work. I can help you with that. So you can feel
Okay.
free to mail me regarding that. But do try to shortlist areas because I don't want to superimpose areas by myself because I would end up forcing you into my area. That is something that I don't want. Shortlist areas based on your interest and then mail me those, and then I'll try to see if I can help in deciding which one would be better for you.
Okay, sir.
Fine.
Thank you.
Okay. Any other feedback query or anything in general? Prasad Rao, anything from you with regards to the feedback on how we could improve this or improve this live session in particular, or how I could improve? Okay, you're typing. Good session. Okay, fine. Thank you for tuning in, and I'll be wrapping this session. Okay, you both are typing. Thank you. Okay, thank you. Thanks for tuning in. I'll be wrapping this session right here. Okay, bye bye. Thank you.